Section 10.1 is on exponential functions. So like I was saying, this is all new stuff. Everybody can do well on this. We're going to learn something cool in this chapter that's called logarithms. Have you guys seen logarithms before? Totally new. So it's a concept that all of you guys can ace. We are very good. You know, typically people do very well on that test. Yes? Sure. All right, so exponential functions. So it says the function f of x equals b to the x, or f of x equals p times a to the x, is going to be an exponential function. The base is a constant greater than 0, not equal to 1, and the exponent x is the independent variable. So there's a lot of stuff going on there. Basically, you can't have something that looks like y equals 1 to the x, because if you did a t-table for that, what would every y value be? 1. Okay, that's not interesting. So that's why we say that the base cannot equal 1. Okay, so let's do an example. So if we have f of x equals 2 to the x, and I ask for f of 3, what that means is we plug in 3 for x, so we have 2 to the 3. So we end up getting 8. 2 times 2 times 2 is 8. Okay. So if I had something like f of 3 over 2, it means 2 to the 3 over 2. And we did this way back when. Okay, so we can write this in another form without using a calculator. So you could write this as the square root of 2 raised to the 3. Do you guys remember that? So like the top number is your power. The bottom number is the type of root that you have. Okay, but I'm just going to end up graphing this in the table below. So I actually want to know what the decimal is anyway. So if you guys have your calculator and you can put this in, check to make sure you get the right answer. So you should do 2 raised to the 3 over 2. And some of the calculators have what I call fancy font, and it will actually raise that power up in the sky, and then you'll see that the 3 over 2 is the whole power. Some of your calculators do not have that, in which case you're going to need parentheses around it. Okay? Yeah, what'd you get?
You can, well, I just wanted to say before that you can change it if you press mode and go down to macro.
Oh, really? Cool. I don't know if all of the calculators do that, but maybe.
The number that I got was 2.828.
Yep, so I'll say 2.83. Let's go with that. All right, so the next one, f of negative 3 over 2. So that just means we have 2 to a negative exponent, which is totally fine. A negative exponent means that we have 1 over 2 to the 3 over 2. And we could write that with a root and so on. So when you find this, you should get 0.35. I would probably just put it in your calculator like 2 raised to the parentheses negative 3 over 2, like that. Okay, so you should get 0.35. And then pi, so 2 to the pi, put it in just like that, 2 raised to the pi. Do you guys know where the pi button is on your calculator? Yeah, it's underneath like the cursors over there. So you do second and then hit it. And that would give you 8.82. Did you guys see the Pi Day pictures up here? I fixed my bulletin board, all the new stuff's over here, all of your smiling faces. All right, so it says use the information from above to fill in the following t-table and graph this. So we want to know what these exponential functions look like. Anybody have any guesses? Have you guys done exponential functions before? Yeah, and most of you guys are kind of doing it. It's going to look like this in the end, okay? So let's see why. So if I have 0, then that's going to be 2 to the 0 power. And we know 2 to the 0 power is equal to 1. All right, and then 2 to the 1, well, 2 to the 1 is 2. So right now I have the point 0, 1. Oops, I'm off a little bit. 0, 1. And 1, 2. Okay, and we found 1.5. 1.5 was the 3 over 2 one. It was number 2. 3 over 2 is 1.5, right? So when we did 2 to the 1.5, that's how we got the 2.83. 2 to the 2 is 4. How about 2 to the negative 1? Yeah, it's 1 over 2. Do you guys remember that? 2 to the negative 1 is 1 over. A negative exponent means 1 over. So 1 over 2 to the first. So it's 1/2 or 0.5. So let's graph some of these points. So we have 1.5, 2.83. Oops, 1.5, 2.83, somewhere around there. 2, 4. Negative 1, 0.5. Negative 1.5, 0.35, so even closer to the axis. Negative 2, 2 to the negative 2. Yeah, 1 over 2 squared. So 1/4, which is 0.25, so even closer to the axis. Okay, so let's think about it. Even if I had like a negative 100, 2 to the negative 100, you guys can try that on your calculator, so go ahead and try it. Your calculator might lie to you. Did you know your calculator lies sometimes? Oh, it told you it's okay. Try 2 to the negative 1,000. Yeah, what did your calculator tell you then?
Nothing.
It says it's 0. But we know that that's 1/2 to the 1,000. Yours says error.
It's incapable of calculating
Yeah.
any number more than about a Google. So
Exactly. The calculator can't handle that much information. It can't handle that many digits. So the bits and bytes and so on of a calculator, the memory of a calculator is important. So it can't hold that. So we have 1/2 to the 1,000. It's telling us it's 0. It's not really 0, but it's really darn close to 0. Is it ever going to reach 0? No, it won't. So we're going to have a horizontal asymptote. So it's going to get closer and closer to 0, but it's never crossing this. So it's close to it. Oh, man, my pen's not calibrated right, so I'm like off. It's driving me nuts. Okay, so it's really close to it, but it's never going to cross. So we have a horizontal asymptote at y = 0. Okay, but are we going to have a vertical asymptote? No. So there's nothing on the right-hand side. We just keep getting bigger and bigger and bigger. Because we can plug in like 100, 1,000,000, 1,000. We get results, right? So I'm never getting closer and closer to something on the right-hand side. Okay, so that's what we call exponential growth. Does that make sense? It's getting bigger and bigger and bigger.
because each time it doubles.
Yep, exactly. Each time you plug in a new x value, one bigger x value, you're doubling the result from before. All right, so let's do the next one. So if I have 1/2 to the x, okay, well this time every single time as you add another x value, like the x values get bigger, you're halving it. You're making it smaller each time, right? So if I had 1/2 to the 0, that's 1. 1/2 to the 1 is 1/2, so 0.5. 1/2 to the 1.5 I gave you is 0.35. 1/2 to the 2, right? 1/2 to the 2 is 1/4, so 0.25. A lot of these numbers are the same. And the reason they're the same is because 1/2 to the x could actually be written as 2 to the negative 1 raised to the x, which is the same as 2 to the negative x. So any x value we had before, so if I had x = 1, I got 1/2. Well, if I had x = -1, that's how I got 1/2 before. Does that make sense? Do you guys see the relation? So what this ends up doing to our graph is it flips it over the y-axis. So you can try all these values, like if I have 1/2 to the -1, that flips it over. It becomes 2/1 to the first, which is 2. And 1/2 to the -2 becomes 4. So when we graph this, I still have 0, 1 that I had before, but now I have 1.5 instead of -1.5 that I had before. And I have 1.5, 0.35, and I have 2.25, -1, 2, -1.5, 2.83, -2, 4, and pi is really tiny, 0.11. So now it's the opposite direction. So we call this exponential decay. It's getting smaller. Okay, so for our exponential growth, both of these, as long as it was in the form y = some number, b to the x, both of them went through that 0.01, right? So we're both through 0, 1. But growth got bigger as I read it like a book left to right, right? We read all books from the left side and we go to the right side. Jacob, are you with me?
Yeah. I'm just
Okay. All right, so what was special about the b value on our exponential growth? It was a whole number, so she's saying it was 2. Could it be like 1.5 or 2? Or 2.5 or something? Yeah, it could be.
It's the constant.
It's the constant. What do you mean by that?
Like every time you plug it in, you're getting the same number.
It's the thing that stays the same as you're plugging it into the calculator. It's the thing that we're multiplying by each time, right? As we plug in a bigger x value. Yeah.
It's greater than 1.
It is. It's greater than 1. Okay, so that will be true on this exponential growth. Do you guys see how b is greater than 1? That's what's important on this exponential growth. Okay, but exponential decay, we still go through that point 0, 1, but now it gets smaller. Okay, so that's still going to look like b to the x, but now b is going to be a number that's between what two numbers? Yeah, it's between 0 and 1. We're not actually going to have negatives, because if I had like -2 to the x, that gets really weird. And the reason is because of those fractional exponents. Like if I had -2 to the 1/2, ooh, -2 to the 1/2, that's the square root of -2, right? That's not a real answer. Okay, so that's why we say that our base can't be a negative number. It's not going to be like a continuous curve. Okay, so exponential growth, exponential decay, both of them have horizontal asymptotes at y equals 0, right? Could we have exponential growth and exponential decay? Could we have exponential functions that don't have a horizontal asymptote at 0, but instead somewhere else? Sure. Do you guys know how our graph would be adjusted? Yeah, like maybe you have b to the x, and then you have like +5, -5, something like that. It's shifted up or down. Does that make sense? Do you guys remember when we talked about transformations? Right, so we could have things like that as well. All right, so horizontal asymptote, it's the line that it gets closer to as we plug in, like x goes to 1,000,000, x goes to -1,000,000, and so on. All right, so find the exponential function f of x equals b to the x whose graph is given. So a couple of these, this first one I think is pretty easy. So we want to look for points that it's going through. So it's going through 0, 1, and it looks like it's going evenly through 1, 3, and it looks like also 2, 9. Now, almost all of these are going to go through 0, 1. They will as long as we have this like y equals b to the x thing going on, right? Does that make sense why it would go through 0, 1 if I plug in 0 for x, b to the 0? That's equal to 1. Okay, so that 0, 1 is not the interesting point that we're going to use. We can use any of the other points. So let's use that 1, 3. Let's plug in the 1 for the x and the 3 for the y. When we do, we get 3 equals b to the 1. So do you guys see? B is equal to 3, exactly. So our function that we have graphed is y equals 3 to the x. So you can write it with a y or you can write f of x, it doesn't matter. Okay, that's the function, done. So let's do it on this one. We notice that this first one was growth, this next one's decay. So our base is not going to be like 3. It's not going to be a number bigger than 1. It's going to be a number smaller than 1. So we again have that 0, 1, but now we have -1, 4, and -2, I don't know, -2, 16. We look for places where it's crossing exactly on those like corner points. So if we have y equals b to the x and we plug in, let's say, -1 and 4, I have b to the -1 is equal to 4. So someone in the first class said b equals -4.
B equals 1/4.
Yeah, b actually equals 1/4. It's not -4. Do you guys see that? Because it's b to the -1, which means 1 divided by b is equal to 4. So we got to do some moving around. So we're going to multiply the b over. So we get 4b equals 1. So we end up getting b equals 1/4. And that's our answer. So, well, I guess it's not totally our answer. I should write my final answer as that function, right? So you can write f of x or y. Y equals 1/4 to the x. So if you were taking like some kind of standardized test, they may not write that answer that way. 1/4 to the x, they might write it as 4 to the -1 raised to the x, which is 4 to the -x. So look for things like that. Know how things are connected, right? 1/4 to the x is really the same as 4 to the -x. So you might see weird things like that. Okay. Feeling pretty good about this?
For a test, can we write it as e or like
Yep. Yep. All right, so sometimes it's not just a b value to the x, like the base raised to a number. Sometimes it's like a number times the base to the x, okay? So like p times a to the x. Let's try these ones. Okay, so these ones do not go through 0, 1. This one goes through 0, 5. And we want to look for other places where it looks like it's going through evenly. It's kind of hard to tell. Looks like maybe over here on the left. Yeah, -1, 10. And we have to use both of these points. I think I forgot to do this in the first period. They're going to be totally confused. This is the first time I've done this problem today. So, whoops. Didn't even tell me I skipped it. Just let me skip right past it. All right, so let's use our y equals p times a to the x. And this time, let's actually use the one that's on that y-axis. Let's use the 0, 5. For these ones, this will be the most important point. If you do that one first, it will help you out a lot. So when we do that, we're going to have 0 for x and 5 for y. So we get p times a to the 0 is equal to 5. Do you guys see why we like doing this? Yeah, the a to the 0 is 1. So what's p? 5. Okay, so already we have part of it. So we have y equals p times a to the x, but we know that p is 5. So we have y equals 5 times a to the x. Okay, now we use any other point. So let's use that -1, 10. So I'm going to have 10 equals 5 times a to the -1. So I get 10 equals 5. A to the -1 is 1 divided by a, so I'm going to write 5 over a. Right, 5 times 1 over a. And I multiply the a over, and I divide, so I get 5 over 10, which is 1/2. So our final answer is y equals p, which was 5, a, which is 1/2, to the x. Done. Okay. So you actually cannot combine those two things. You can't combine your 5 and your 1/2, because what we're doing is we're halving our result each time we make x bigger, right? So we can't combine the 5 and 1/2 and do 5 halves, because that makes it bigger, right? That would be exponential growth if we had 5 halves to the x. Do you guys see that? Okay, so don't do that. And it also has to do with order of operations. You would have to do your exponent before you can multiply. That's why we can't combine those. All right, so same idea on this one. So we have 0, 6. Do you guys see what p would have to be then? P is always that y-intercept, yep. And then we have maybe this point here, 1, 4. Yeah. So it's not going to be a nice one. So let's try it. Try it along with me. So if we start out with a y equals p times a to the x, and we plug in the 0, that's how we get 6. So p is equal to 6. So if you just know that it's the y-intercept every time, that helps. So we have y equals 6 times a to the x. So now if we plug in 1, we get 4. So Jacob, what do we get for a? So 4, 6, which he reduced to 2/3. Good. So our final function then is y equals, our p was 6, our a was 2/3 raised to the x. That's our final function. Feel pretty good with that? All right, so let's decide if these next ones are growth or decay. So what we're looking for is the base of the exponent. So we want to know if that number is bigger than 1 or less than 1. So 3/4, less than 1. So is it going to get bigger or smaller? Smaller. So this is decay. And you could find 2 points in the graph. Sometimes I do like a little t-table. So if I plug in 0 and if I plug in 1, I can find those different values. Do you need homework, Abby? Sorry. All right, so if I plug in 0 and I do 3/4 to the 0, I get 0, or I get 1, right? 3/4 to the 0 is 1 times 8. So when I plug in 0, I get 8. When I plug in 1, I get 8 times 3/4, which is 6. So do you guys see if you had 0, 8, and then you had 1, 6, that's why it's going downwards, right? We get that. So you can find a couple points if you need to. I think I had you guys find a couple points on your homework. Or I'm having you find a couple points. All right, how about this next one? Yeah, it's growth. And again, 0 and 1 are the best points to plug in. If I plug in 0, it's kind of nice because this 1.05 to the 0 is 1 times 10. So we get 10. And if I plug in 1, 10 times 1.05. What do I do when I multiply by 10? Move it over, so it's 10.5. And it makes sense because it's getting bigger, right? So we had 0, 10, and then when I plugged in 1, I was a little bit higher. So it's growth. Okay, still feeling good about this section? It's pretty easy. All right, so the next one. So it says you can model growth or decay by a constant percent increase or decrease with the following formula. Okay, we do these types of things all the time. We multiply by percentages all the time. So if I'm going to the store and I see that something is 15% off, I don't take 15% of the price and then subtract. Instead, I'm smarter than the system. And I say, oh, that shirt's 15% off. I'm going to multiply it by what number? No, 0.85, right? Ethan said it, 0.85, because you're paying for what percentage of the shirt? You're paying for 85% of that shirt. Does that make sense? So if I have taxes, and the sales tax is 7%, what do I multiply my final amount by? I multiply by 1.07, right, to get my sales tax. We do this. These are where these come from. So if I have a percent growth, I'm adding. It's a number bigger than 1, so I'm doing 1 plus the rate. But if it's a percent decrease, I'm subtracting. So on this first problem, it says Grace invests $5,000 in an account that pays 6.25% interest per year. So in math, we write that as 0.0625. So how much money will she have in her account in 10 years? So the formula is the amount after 10 years is the principal amount. I don't think of principal, I think of put in, P, put in. She put in $5,000 into an account that was 6.25% interest, so I do 1 plus 0.0625, raised to the 10. So what I put in my calculator is 1.0625 to the 10, and then multiplied by 5,000. Luckily, your calculators do this all together. So you could have even left that plus in there, and it would still be okay. So we get $9,167.68. So Kyle Sweetko was make me laugh in first period because he was like, what bank would ever do that? Banks don't do things like this. Like, they don't say, oh, at the end of the year, we're going to give you 6.25% interest. And you never put any money in throughout the year, right? This is just, you know, like, things don't really happen like this. So this is not a realistic example. We'll do harder ones later. Okay, so number 2, so city population, which was initially 18,000, has been dropping at a rate of 3% per year. Write an exponential function and use the function to approximate what the population will be in 20 years. Okay, so now we're losing people. Okay, hopefully they're just moving away, the city population. I don't want this to be a morbid example where people are dying in the city. They're moving. So we're finding how many we have in 20 years. So we started with 18,000 people, and we have 1 plus 0.0, oh, not 1 plus, right? 1 minus, because we're losing 3%. For 20 years. Doesn't that make sense that we're multiplying by 0.97? We have 97% of what we had each year before. So you could do this one thing at a time. You could find 18,000 times 0.97 one time to find after 1 year. And then take that amount and do times 0.97 again to get the second year. Okay, so this is where this is coming from. So we're doing it all together. And our population ends up being 9,788.298 people. Would you ever write that as your answer? No. So we're going to write 9,788 people. Round up or round down, it does not matter to me. All right. Is this making sense? Do you guys get it? Now I made a typo in one of these problems. It kind of makes me laugh. So let's see if we get to this next one. Yeah, this next one. In 2006, about 1 billion people used the internet. The number increases by 9.5% annually. Do you guys know the population of the Earth?
7 billion.
7 billion. I've clearly done something wrong on this problem, right? But I think 1 billion people probably did use the internet in 2006, so I don't know. And I feel like I looked up those numbers too. So I don't know. We're going to make it 1 million because it doesn't make any sense for 9.5 billion people to use the internet in 2007 because we don't freaking have 9.5 billion people. So I've clearly written something wrong. So we're going to go with this. All right, so make it 1 million. All right, so write an exponential growth model to model the situation. So we're going to have the amount after t years is equal to our initial amount, which I'm going to say is 1 million. And we're increasing by 9.5% annually. Yeah, 1 plus 0.095, right? 9.5%, 0.095. So I'm going to do 1.095 to the t. So then it says, well, about how many people will be using the internet in 2020? So do I plug in 20? No, I plug in 14 because I started in 2006 and I'm going to 2020. So I'm going to plug in 14, so I'm going to have the amount after 14 years is equal to 1 million times 1.095 to the 14. So we end up getting 3,562,851 people. Since it's people, we're not going to round to decimal. Okay, are these making sense? Do you guys get it? All right, so we'll skip that last one. Let me pass out your homework.